Good evening, everyone. This is Fahim, and this is going to be my first recording in hopefully a string of videos and uploaded clips that I will be posting to a playlist on YouTube that will hopefully demonstrate my knowledge as a data science student at Kennesaw State University. Today, we are going to be taking a brief overview over a Latin squared randomized blocking design that we learn in experimental practices. Now, I'm going to be bringing up my Word document here so we can look at the brief overview that I managed to type up. First, what is a Latin square design? There are many varying designs in experimental design, and this one has some really big strengths tacked to it, but then there's going to be one very big weakness that really holds it back from being observed and used more in higher end studies. A Latin square design is a type of experiment or study where we have individual treatments that must be randomly assigned to each of our subjects the same number of times. And the reason we have to do this is to control the variation between something known as a nuisance factor. What is a nuisance factor? To give you an example, I conducted research at Savannah State University during my undergraduate research where we had to sample phosphate and nitrate, which are chemical compounds, sample their concentrations across open water, such as oceans and different environments. Now, the biggest problem that you might encounter is you have to specifically plan when you're going to be taking these samples because of tidal stages. Let's bring up Excel here. There's a couple of tidal stages. You might have a high tide, let's say a low tide, a neap tide, and I'm sorry for the clicking from my keyboard, a neap tide, and I think a spring tide. Yeah. Now, these are all factors which you have to take into consideration when sampling, because if you take a sample during a low tide, you might have residue at the bottom of your water and it might inflate your samples. Then if you take it during a high tide when the levels are rising, you're going to have or observe less concentrations of a specific sample such as nitrate and phosphate. But Latin square is the type of design that allows us to work around that. It is very simple to understand and extremely simple to execute because you're able to block factors such as, let's say, these tidal stages when designing an experiment. There's one very big drawback to it, though. It has one extremely restrictive condition, and that is the number of levels of your nuisance factor have to be the same as the levels of treatment. So, if this still is confusing you, think about your first car. Just stick with me here. Your first car might have what it takes to get you to work and back. It might take some friends to an outing or two, but you probably wouldn't use it to travel hitchhiking in the Appalachian Mountains or do any workhorse. That's going to be maybe once you have a career, once you get a better car, you're going to use that car to do those types of things. But it's great to learn the ropes of experimental design, and I will be, of course, I can pull it up here, demonstrating a problem in Minitab. Now, you can realistically perform any type of experimental design in any software of your choosing. You can do it in R, you can do it in Excel, but I'm going to be using the Minitab web app because of its ease of functionality and because I think it's the best at displaying to you guys what exactly I'm doing without having to type a bunch of code at the same time. Let's take a look at the problem right here. We are given a specific study where we are mailing out 3 different designs for a specific brochure to different regions. We have design 1, 2, and 3 of a brochure. Here are all our regions, and let's consider these counts, these numbers in the blocks of the table as the number that we are receiving back, the number of surveys. We are aware that the regions we are mailing them to is a nuisance factor. Some people in these regions might consider our surveys as spam. They might not read them depending on where they're brought up from. They might throw them in the trash, or they just might choose to do it and forget to send it back. Whatever the specific case in each region, we know that that is influencing the number of recordings we are receiving back. We are not concerned about that. We want to know is the design of our brochure the 3 that we are sending out, is that the factor that we should be accounting for? Is one design better than the rest? Are they all equal? So how do we perform this? Let's go back to Minitab right here. And the easiest way to start off is to perform a ANOVA, general linear model, general linear regression over our data set. We're going to include design type, the region, and the sample number in the table. So for design type, we have 3 different brochures. We have 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, and 3. The regions they were sent to. Now, one of the drawbacks using the Minitab web app, unlike SAS, you can't enter, at least in my understanding, you can't enter alphabetical integers. You can only enter numeric. So let's say this is northeast, southeast, southwest, whatever it may be. And these are going to be our samples for each corresponding design type and region. When we look at the residuals for our test, we notice that number 1, we're probably going to need to transform this data set. There's something going on here where some of the characters or values are grouped together here. It doesn't look like it follows the trend of normality. Let's see. There we go. When we look at our Anderson-Darling tests of this original data set, we have a significant p-value, which is not good for a test of normality. It looks like we're going to have to perform a transformation on this data set because these values are clustered. It doesn't appear to follow a normal trend, and our significant p-value is not a good sign at all. So if we transform this data set right here with a square root transformation, that's typically your go-to when performing transformations on a data set. Our p-value looks much, much better. There's less clustering, there's less grouping towards the middle right here, and it generally follows a normal relationship on our residuals. Now we have to go back and now we can go back and analyze our general linear model for our squared data set. If we scroll up here, we're going to be given our f values and p values, which will tell us whether or not our design for the brochures is a factor that is influencing our results. We're going to go back to the original data set for a moment. We'll notice that we have these f and p values. We have significant p values and very high f values, but those are increasing when we do our transform data set. What is going on here? Why is it that we get a better data set that will hopefully more accurately give us better results? Why is it that we're still observing high p values, low p values, and high f values? This is because we have confirmation now that the design type for the brochures is a factor that is influencing our data set. This is very good. It is not just region that is being the nuisance factor. We are also observing something with our design. What do we do now? We now have what we need to perform a one-way ANOVA test. Go back to our transform data set, perform a one-way ANOVA, and do pairwise comparisons between these groups. We see that between the groups, we have a low p-value for our designs and a relatively high f-value. This is very good. We now have a confirmation that there is differences between these 3 types of brochures. We're able to do a 2 keys pairwise comparison where we see that design 2 has a high mean and it is different. It is differently grouped in designs 1 and 3. We can go down to Fisher LSD right here where we're observing the exact same thing. Confidence intervals that do not cross this boundary of 0, that do not contain this value of 0, are significantly different. And both of those contain design 2 for the comparisons right there. This is the grouping information using the Fisher LSD method and our interval plots right here. It's a very simple method, and we have all of our information that we need to confirm that not only are there differences in our designs that we were not accounting for when taking region into account with our original general linear model, but once we isolate that, perform a one-way ANOVA, we have confirmation that design 2 is our best design, and we can hopefully employ that in future research. I hope that my perspective was insightful, and I hope to be back with another video soon.